Good morning. My name is Ivan Pogorelov. I'm a PhD student at the University of Innsbruck. Unfortunately, today I cannot attend in person due to some visa delays, but nevertheless, I would like to present our work about trapped ion quantum computing and quantum error correction experiments we did. The talk will consist of two parts. Since I come from an experimental group, the first part will be devoted to our hardware setup. I will just briefly describe and show some pictures of the hardware and also give some information about our gate mechanisms and some performance values. In the second part, I would like to present our work on quantum error correction, where we demonstrate fault-tolerant universal gate set with two logical qubits, and also some background introduction on error correction. So our project is called Action, and the main idea of the project was to make a step from standard lab environment, which you can see on the left, to something more industrial and standardized, and you can see our setup on the right. We really tried to make it more compact and modular and remotely controllable as much as possible, so that, ideally in the long term, such a setup can be standing somewhere in the data center and be accessed remotely without requirement for constant high maintenance and so on. As you can see, the setup sits in two 19-inch racks, and it doesn't need any special lab environment, doesn't need any water cooling or cryo cooling. You just need a power plug and LAN cable to make it work. All the modules are inside these two boxes. So except for the rack integration goals, we also wanted to work with medium-long ion chains, maybe up to 20, 30 ions, and investigate performance limitations there, so how far we can push it. As I said, I won't be going too much into details how the setup works exactly, but I want to show you some, some photos of the setup so you have a feeling of what this experiment is about. So, for example, here you can see an example of our compactness. All the optics here is packed into this drawer, which is a breadboard, 19-inch rack compatible breadboard, and allows us to really shrink the size of the setup. You can also see some cassette plug-in modules. So they're sitting right here, and we can pull them out separately without disturbing the rest of the setup in case we want to do some realignment or adjustments or replace a unit, something like this. The main part of the setup is ion trap. It's sitting inside this trap drawer inside the vacuum chamber in the middle. The trap drawer itself is sitting on vibration isolation stages, which we use instead of a massive optical table, as in standard lab environments, which also helps us to decrease size requirements quite a bit, although vibration isolation performance is similar. So that's our trap inside the vacuum chamber. It's an order of centimeters large, and all the action is happening inside the trap where we actually have our ions. We're working with calcium-40 ions. You can see electronic level structure in the picture, and our qubit is encoded in D5 half S1 half states. So that's an optical transition at 729 nanometers. That's why the qubit type is called optical, and we use a narrow band 729 nanometers laser to manipulate this qubit. So for detection, we use this 397 transition from S1 half to P1 half. And if ion is in ground state, in our one qubit state, it scatters light when we excite this transition, so we can see a bright spot on the camera. While when it's in this D state, it doesn't scatter anything, it does not participate in this transition, and we can see a dark spot. So that's for one ion. If we want to detect several ions, we usually use a EMCCD camera, and you can see an image of an ion chain here. And actually, these two empty spots are not empty, there are ions there. They're just in D state, so we cannot see them. And when we want to detect the ion string, we usually assign a region of interest to each ion on the camera, and set a discrimination threshold for each region of interest. And then once we have counts coming from ions, if counts are above the threshold, we count it as bright, so 0 state, or count it as dark if it's below the threshold. It's also important for us to be able to manipulate ions individually, and for that we need some kind of single ion addressing setup for 729 nanometers light. So for that, we use two acousto-optical deflectors crossed at 90 degrees. That's a device which deflects the beam when supplied with RF power. So if we supply both of them with RF power, they deflect our beam. And when we change the frequency of the RF drive, it actually moves our beam along the ion chain, and that's how we can scan the ion chain. If we supply several frequencies simultaneously, we can also address several ions simultaneously, although we mostly do two to make it more simple. It's also important to notice that that allows us for individual phase and power adjustment for each ion we address with this setup. So for current setups, ion trapping setups, substantial problem for single ion addressing is optical crosstalk. That's when we excite one of the ions, neighboring ions also see some leaking light, which is unwanted. And here I present a characterization of the optical crosstalk in our system. That's a huge 50 times 50 matrix. And I zoom in this part here. So you can see some numbers here, and that's ratio of Rabi frequencies. For example, if we excite ion 16, ion 17 sees 3.5% of Rabi frequency, and also sees some unwanted flops, which we want to minimize. And actually, the maximum number in this whole huge matrix is 3.5%, while on average it's 1.2. So that's several times better than in our previous setup, and it helped us to boost performance quite a bit. So after we can address single ions, we can discuss what gates in terms of quantum information we can do. So for single qubit gates, we usually do resonant interaction with our qubit transition, which drives Rabi flops and results in rotation around an axis and XY plane of a Bloch sphere. So the axis direction we can control by phase of the pulse, and the length of the pulse controls rotation angle. For Z rotations, we can do off-resonant excitation, which induces AC Stark shift, but we can also do it virtual, which is quite popular, I think, in different setups nowadays. We just correct phases of subsequent pulses acting on a certain qubit, which makes it a perfect operation. It has a fidelity of 1, although it's completely equivalent to the one we do physically, but it's a win-win situation, basically. So with this, we can do arbitrary single qubit operation. So for 2 qubit operations, we use phononic modes to mediate interaction between ions, and we use Molmar-Sorensen type interaction. So in this picture, you can see energy structure for 2 ions and 1 phonon mode, which is presented by this phonon number. We need a bichromatic beam to drive this interaction, and it's this red and blue frequencies here, and they are both slightly detuned from driving a phonon mode. But together they add up to a SSDD transition. And if we now scan the interaction time, you can see that population oscillates between SS and DD. And once gate parameters are chosen correctly, so here we will have a maximum entangled state, and also the phononic mode will be decoupled in the end of the interaction. That will be so-called XX gate. It produces a Bell state, and also it's equivalent to C0 up to local rotations. It's also important to notice that we can entangle any pair of ions in our chain. So it's like all-to-all connectivity. As for the fidelities for our operations, they're given in this slide. I haven't really talked about how we do state insulation, but fidelity is around 99.7, as well as for camera readout and single qubit operations. Single qubit operations we characterize with randomized benchmarking sequences. For 2 qubit gates, it's around 97.5 on average, because fidelity varies a bit from ion pair to ion pair. And we deduce it from full register GHZ state fidelity. So these fidelities are given for 16 ions, and usually when we have more ions in the chain, fidelity drops a bit, while if we have fewer, it's a bit higher. So in case we want to make an experiment which only involves 10 ions, we can boost them a bit. What is also quite important, in my opinion, is to keep fidelities constant over time. And for that, we run a set of auto-calibration procedures. It's not very important what exactly we do for the scope of this talk. I just want to point out that when the set is running, operator of the setup doesn't need to do anything manually. Fidelities are just kept constant. And we also try to design the operations in such a way that when we increase the length of the chain, the size of the chain, the time spent in auto-calibration does not grow significantly. And For example, for 16 ions, we only spend 20% of time for calibrations, and 80% of time we can measure, run some circuits, and so on, which is quite a high duty cycle in my opinion. So that's it about the setup part. Now I would like to present experimental results where we actually demonstrate fault-tolerant universal gate set for 2 logical qubits. I will start with brief introduction of some terms from quantum error correction. So we will be working with STEAM code, or 7-qubit color code. It encodes 7 physical qubits into 1 logical qubit, and it has a distance of 3. So to introduce stabilizer generators, we will split this triangle into 3 plaquettes, 4 qubits each, and each plaquette has X and Z stabilizers associated with it. It's just X applied to all the qubits of the plaquette. And for logical operators, we can define them as X acting on all the qubits or Z acting on all the qubits. So logical state will be eigenstate of all the stabilizers. So it's a distance 3 code, meaning it can correct up to 1 arbitrary error. And we can detect it by measuring stabilizer values. For example, if an error happens here, this Z stabilizer will flip its value and signal an error, which we can later correct appropriately. So it cannot correct 2-qubit errors because, for example, in case errors happen here, the same syndrome will pop up and we will not be able to distinguish these 2 cases. That's why we can only deal with 1 error, and we should keep this in mind for the future slides. Another problem can be, we can correct up to 1 physical error, but we also should take care of the error propagation. For example, if we want to prepare a logical 0 state with the circuit given here in the slide, we should notice that some errors, when they happen early enough in the circuit, can propagate through CNOT gates according to this schematic, which will result in 2 physical errors in the end of the circuit on our logical qubit. And we cannot really detect or do anything with this because the code is not designed for this. So such a circuit design is not fault tolerant because single physical error will lead to an uncorrectable logical error. And we should do something with this. All there are proposals how to fix this. For example, we can add this verification circuit, which has additional auxiliary qubit, usually called flag qubit. And this flag qubit is meant to catch some dangerous error propagation. For example, again, if the error happens here, it will also propagate to a flag qubit. It will flip it. And once we measure it, we will be able to discard the whole state because here it becomes uncorrectable and we can no longer use it. But if we only accept states which do not raise the flag qubit, we will actually end up with a situation where all errors are correctable and single physical error always leads to a correctable error. And the circuit will be fault tolerant, and that's the key idea of what we will be doing. So once we prepare the logical state, we can also think about how to make gates in a fault tolerant fashion so we do not propagate errors. And fortunately, in color code and 2D color codes, Clifford gate can be implemented transversely and thus fault tolerantly. So when I say transversely, I mean that if we want to apply a certain Clifford gate to our logical qubit, we just need to apply physical gates to all the qubits, one by one, and in this way we will implement a logical gate. Sorry. In this case, error will not propagate because they are not connected during this gate in any way, and will also stay fault tolerant. And the same will happen for CNOT gate, which is also part of a Clifford group. Here, an error can propagate, but if you notice here, it propagates from one logical qubit to another logical qubit, and we can correct up to 1 error on each logical qubit. Only 2 errors on 1 logical qubit we cannot fix. So this is also fault tolerant due to transversality. However, to make a universal gate set, we also need something non-Clifford, for example, T-gate. And due to Easton-Neal theorem, we cannot have all the gates simultaneously transversal in one error correction code. So we need to do something else. For example, we can do so-called magic state injection, which is in some sense gate teleportation. So here we will prepare a specific magic state. And then we will teleport and inject this magic state into our circuit to make a logical T gate on our target qubit. Main problem here is that this magic state is relatively hard to create, and also we need to make sure we create it fault tolerantly so it doesn't have dangerous error propagation. We'll do it in a similar way we treated logical zero preparations. We'll prepare it non-fault tolerantly, and then we will introduce a couple of flag checkups, which will allow us to discard states which have dangerous error propagation. And after that, we will inject it into our circuit to make a logical T-gate. So once we do this flag checkups, which actually need quite a bit of qubits, 8 flag qubits, we will guarantee that this magic state prepared has at most one error, which is corrected. Yeah, that was brief theory introduction. So now we will go through the same operations, but with experimental results. So state preparation, single qubit gates, 2 qubit gates, and magic state injection. So first part here is non-fault tolerant state preparation. And here we plot how often each error occurs, and we sort them by weight of the error. So those are no errors at all, 1 physical error, 2 physical errors, and 3 physical errors. And you can see that these two are comparable. So 1 physical error and 2 physical errors, while this group is uncorrectable. So we need to get rid of this as much as possible, otherwise we cannot use our state anymore. We can try to mitigate this ratio by adding this verification circuit. And once we discard all the states which raise our flag qubit, we can see that the portion of uncorrectable errors decreases substantially in our favor. And that's actually what we were looking for. It gives us a logical fidelity of around 99 for the state preparation. And of course, we lose a bit in state generation rate because we do post-selection, but still we end up with high quality states. There is also some theoretical comparison of the circuit with quite a simple model with just a polarizing noise. You can see the numbers relevant for the theoretical model here. And theoretical results are shown in these lighter colors. And also in the future slides, they will be shown in lighter colors. And you can see the agreement is quite well, although the model is quite simple. So after we prepared our logical state, we can start applying gates. So we start with single qubit gates. As I said, we can do single qubit gates from Clifford group transversally. So we just apply it to each qubit. And like this, we can prepare different Pauli states with an average fidelity of around 99. Then we can apply 2 qubit gate. So for that, we need 2 logical qubits, which we prepare separately one by one here. Apply some single qubit rotations to change the input state of the CNOT gate. And CNOT gate itself, we can apply transversally because it's also a part of Clifford group, which is transversal in SKIN code. And resulting Bell state and infidelities for different input states for the CNOT, you can see on average fidelity is around 89%. The last part, which is required for the universal gate set, will be magic state injection and T-gate, which starts from preparation of the magic state. So you can see this heavy circuit here. As I said, it consists of non-fault tolerant preparation and 2 flag checkups. One is measuring in eigenbases, and second one is error detection of all 6 stabilizers. And here you can see that after each step, infidelity decreases down to 99.4%, which is actually a bit higher than if we were doing it physically. Because of this heavy post-selection, we have only 13% survival rate. But again, as I said, the quality of the state is much higher. And also it keeps only 1 error, which is correctable. So to do the T-gate, we need to do this gate teleportation. So first we do this magic state preparation. Then we initialize our target qubit. And then we apply C0 and Clifford gate to actually do the T-gate in the end. That looks like quite a resource demanding circuit. So it needs 2 logical qubits, which makes 14 physical qubits in total and 9 flag qubits. And it seems like we need 23 ions for that. But we can actually get away with 16 because once we prepare magic state, we can detect these flag qubits and reinitialize them and use them for logical target qubit. So ions allow for that. And also, as I said, they have all-to-all connectivity. So it doesn't really matter where in the chain these ions were located because we can entangle any pair. So once we did all of this, we have the following fidelities. Here is the process matrix of a T-gate and infidelities over different input states. mean fidelity is around 90%, and survival rate is around 10%, like it was for magic state preparation. So with this, we conclude the universal gate set, because we did single qubit gates, C0, and non-Clifford gate, which is T gate, this one. Well, that concludes my talk. Just to give a brief summary, I showed you our new setup for trapped ion quantum computing, which is sitting into this 219-inch racks, and it's quite compact, remotely accessible, modular, and so on. So we worked with 7-qubit color code, and we had 2 logical qubits where we showed universal gate set, and we also demonstrated that fault-tolerant circuit design substantially improves quality of the states and boosts fidelities. So with this, thank you for your attention, and your questions are very welcome.
Okay, thank you, Ivan. So can I remind people that are in the other room that they can post questions through the app, because we've not had any through the app yet, and I'll get us started. So you mentioned the importance of using the flag qubits when you were doing state preparation, but you didn't mention it with respect to measuring the checks. So can I ask, when you're measuring the stabilizers, do you have anything in there in terms of flag gadgets to check for these kinds of mid-circuit errors that you had in the diagram?
What are you referring to?
So when you talked about
if you're talking about this, for example, right? So we measure all the stabilizers as a flag checkup to filter the state.
Yeah. So I think you said this was error detecting. So you doing an error detection
right. You mean for standard error correction, for error correction cycles? Let's say we have 1 qubit and we just want to. Well, yeah, there are also different ways, I guess, how to do it. But you can also add for stabilizers readout, if you read all of them simultaneously, you can also add some flag checkups. Unfortunately, I don't have a slide for this because we don't really demonstrate repeated error correction cycles in this work. But yeah, you can use them as well.
Okay, thank you. Any questions from the room?
I can hear you.
Yeah. So you mentioned that this is all-to-all connectivity within a chain. This is a question about scalability. And you also mentioned at the very start that a chain can have, you said, between 20 and 30 qubits. Just like as we start to sort of scale up, what is the upper limit of how many ions can fit in a single chain? And then when you lose that all-to-all connectivity between chains, how are you like connecting isolated chains of ions? Larger computation.
Yeah, okay. So first of all, in our trap, we only have 1 chain. I will talk about 2 chains separately, I guess, but the main limitation, I guess, let me show you this slide probably. So first of all, when you want to squeeze more ions, you need more RF power. And at some point, you will just not have enough because they will go into the zigzag configuration. We can probably fit up to 50 ions. And as I showed with this crosstalk matrix, we can have pretty good results for optical crosstalk and good results for single qubit gates in 50 ion chain. Although for 2-qubit gates, it doesn't work that well because of this mostly. So when we increase the number of ions, we have a lot of motional modes, which we use to entangle ions. Once we, let's say, have 30 ions, we have tons of motional modes. And every time you do a gate, you actually need to take this into account. So you need to make sure that all the modes are decoupled. You need to know how you interact with them and so on. And I would say that's the main limitation as I see it, or at least as we practically see it, that the more modes you get, the more complicated it becomes to do a gate, to make sure it's all decoupled and the fidelities are good. There are special techniques like, for example, phase modulation. You can do some kind of complicated gate shapes to decouple this additional modes and deal with the spectrum, but still it limits the performance quite a lot because you need to take care of all of this. So if you have 2 chains, that's not what we do in our trap because we have single blades basically, which are not segmented, and we just trap the whole bunch at the same time. But if you have a segmented blade, you can have several trapping regions, and I don't really think that you can connect them efficiently somehow, although you can do like 2 interaction zones when you do entanglement, and then you just shuttle them either by, flipping them physically or just, moving and merging chains somehow. You can shuttle them in this way. It kind of loses all-to-all connectivity to some extent, but that's debatable, how you define all-to-all connectivity, I guess. But yeah, you can do shuttling. As far as I know, Quantinum is quite successful with this, shuttling approach, many qubits architectures. Yeah, and that's also one of the solutions. Although, as I said, in this experiment, we actually wanted to focus on one ion chain and see how long we can make it and what actually fails. And I would say that addressing doesn't really fail up to 50 ions, but this mode handling is quite complicated, and that's what limits us, I guess, for 2-qubit gates currently.
Thank you very much for the insightful talk and the great explanations. And it's a shame that you were not allowed to come in person. I was wondering if you tried out state preparation by measuring stabilizers directly instead of like running the encoding circuit, and if yes, how that compares to the encoding circuit.
Yeah, that's a good question. I'm not sure. I actually don't have a data for this now. Probably there was some tries, but I don't really remember the results. But yeah, I guess that's a valid approach. But a lot of theoretical work, I think, has been done already on where is the slide? How to make this operation efficient. And I guess, in all these papers, they describe and, compare resource requirements. And I think that's one of the most efficient approaches. But yeah, sure, you can also try that.
Could also scale to large qubit numbers and stay efficient. Do you know this?
This approach?
Yeah, because stabilizers you can measure in parallel, right? So it's very quick, even if you have thousands of qubits, right?
Well, I mean, you can also, if you have several logical qubits here, you can also do it in parallel.
Oh, sorry, I mean one logical qubits with thousands of physical qubits.
Yeah, okay, so I don't really know. As far as I know, the most promising approaches for, fitting more physical qubits into logical qubits are LDPC codes, where distance and number of logical qubits grows together with the number of physical qubits. And I actually don't really know how to do fault tolerance in there. But yeah, I think people are working on it, and they're trying to take care of how to. So I wouldn't really go to high dimensional codes here. I probably would go for LDPC codes if I want to squeeze more logical qubits. Yeah, and unfortunately, I don't know how to do fault tolerance in there.
Okay, thank you anyway.
Sure.
Thanks.
Any more questions? Check the app. Check the app first.
Ivan, thank you so much for that. It's, of course, an incredible tour de force of magic state injection, and just wanted to take a moment to recognize how challenging that is. One question I had, so if you go forward to your error detection circuit, I noticed,
this one?
Yeah, I noticed that you're doing some flag qubit work in terms of the gates between the syndrome qubits. And I was curious if you could just tell us a little bit what the rationale was, what you're looking for in those inter-syndrome qubit gates.
Sorry, I probably.
So you see, for example, you start with +00 in the error detection circuit for the first check there, yeah. And one of the things that you do, you'll note, I noticed that you have a gate between the plus and the third qubit, the zero there. So you're, for example. So some of these internal gates, I think that they're doing flag qubit work, in which case I would love to understand what the distribution of the XZZ results at the end of that were, not just survival rate, in other words. Do you have any thoughts about that, or am I misunderstanding?
I probably don't really get it. So yes, indeed, they have gates in between, and I think this is all. I'm not sure about how, the exact rationale for the design of the circuit. I think it's pretty hard theoretical work. So we were just using the kind of ready-to-use circuit, but as far as I understand, it maximizes the ability to catch dangerous error propagation by doing this interqubit gates, inter-ancilla qubit gates.
So then let me just ask the specific question, which is, did you look at the distribution of XZZ, the measurement results? Not just did they all come out correct, but when they came out wrong, what that distribution looked like?
We probably did. I don't remember. You're just referring to that some flag qubits are catching more errors than others, or?
Yeah. So when I think about that circuit, right, I think that the output of things that are wrong actually tells me where errors are occurring. So it's a type of limited metrology. And I'm curious what you saw. So if you had a slide, I'd love to see it. But if you don't,
right, no,
later,
unfortunately, I don't have it. I mean, it's easy to extract this data, of course, and also all the data is published online on Zenodo. But yeah, unfortunately, I don't have a slide prepared for that. Sorry.
Well, we're out of time now, so let's all thank Ivan again.
Thank you.